So here we have a couple problems involving impulse and momentum. The first problem says a rubber ball and a clay ball both hit the ground at the same speed. The rubber ball bounces, leaving the ground at the same speed with which it hit, and the clay ball sticks. The question is, which ball feels a greater impulse from the ground? So I'll start this problem by drawing a picture. It's always a reasonable way to start a physics problem. So for the rubber ball, we can draw the ball approaching the ground and the ball leaving the ground. So here's maybe V initial. The ball leaves the ground at V final, the same speed, just the other direction. Right, so what I've drawn here is a before and an after, just right next to each other. Okay, and let's draw the picture for the clay ball as well. The clay ball has the same initial setup, so it's the same before. So here's my V initial. But afterward it's stuck to the ground. So here's my after, right, where V final equals 0. Okay, so I'm looking for impulse. Which has the greater impulse? So if I recall, impulse can be defined in a couple different ways. One of them has to do with the area of a force versus time curve, but I don't have any reference to a graph in this problem, so I'm not going to use that. I can also use an F average delta t, but I don't have either of those values here. And the final definition here is that J is the impulse, is equal to the change in momentum for an object. And I definitely have the information I need to find momentum. So let's just draw the momentum vector on each of these diagrams. Remember that momentum is mass times velocity for an object. So the initial momentum for this rubber ball is an arrow that looks like here. This is P initial. And the final momentum looks something like that, P final. And I can do something similar for the clay ball. P initial looks something like this. And P final is 0. So maybe I want to calculate for the rubber ball what is the impulse. So for delta P, I just need to say that's P final minus P initial. Right? And remember, momentum is mv, so I can simply say mv final minus mv initial. So that I can plug some numbers in here. The mass is 0.055 kilograms. The final velocity is 12 meters per second, and it's positive, right? So we'll choose up to be positive. So that's 12. Then we subtract 0.055 kilograms times the initial velocity, which is actually a negative 12 meters per second. And what you see here is that this is actually, these two negatives cancel out, and you get 2 times 0.055 times 12. Numerically that comes up to 1.32 kilogram meters per second. Alright, so that's the impulse for the rubber ball. So now we should ask, what's the impulse for the clay ball? Well, we start with a similar equation, right? J for the clay ball is equal to the change in its momentum. And we can actually guess from here, what's happened for the clay ball is we go from an initial momentum of something that is downward to 0. Right? For the rubber ball, we went from something that was downward to something that is upward. So we expect to see something smaller here. Alright, so that's actually our answer. We can already say the clay ball experiences a smaller impulse, but let's go through the math and see exactly how much smaller it is. Okay, so delta P, we can say P final minus P initial, and again, M V final minus M V initial. Well, we already said V final is 0, so that makes this term 0. Right? So then we just need to plug in for MV initial, so that's minus 0.055 times minus 12 meters per second, since the initial velocity is downward. So we're multiplying 0.055 by 12, which is exactly half of what we had for this, for the rubber ball. Right? So when you do that math, you end up with 0.66 kilogram meters per second. So J for the rubber ball is twice J for the clay ball. So the rubber ball feels a greater impulse. So the second problem here says we have a racquetball bouncing off of a wall at a certain angle, right, 30 degrees to be exact, both incident and bouncing off at that same angle. The question is, what is the average force during this collision? Sorry, the average force is given as 150 newtons. The question is, how long is the ball in contact with the wall? So, if we recall, that impulse can be written as the average force times a delta t. Average force times a delta t. That relates a force we're given to a quantity we want to know, right? We want to know how long, which is a delta t. So this is going to be useful. The other definition is what we used in the previous problem, or another definition is what we used, which is that the impulse is the change in the momentum. Okay, so if we look at this diagram and think about the things we were given, we ought to be able to figure out what the momentum is before and after this collision. So if we set these two things equal to each other, if we say the average force times delta t equals, in fact, I'm going to write it as P final minus P initial, we ought to be able to use this equation to figure this out. So let me label some things on the diagram. What we have here, these arrows, could be initial velocities, right? So maybe this is, velocities. This is initial velocity. Maybe this one is a final velocity. And we could draw momenta here. So let's say this arrow is P initial, and maybe this arrow is P final. Let me take it one step further and break these into x and y components. So to do that, I need to define what I mean by x and y. So I'll draw some axes on here, always a good idea. And now I can break each of these vectors into x and y components. So maybe I have an x component for the initial momentum that looks like this, and a y component like that, so we'll label it as P initial x and P initial y. And I can do the same sort of thing on this diagram. This is P final x and P final y. Okay, so let's write down some things that we know, some known values. So we know the mass, we're given the mass of the racquetball as 0.0427 kilograms. We know the speed before and after. Alright, so that means the magnitude of V final and the magnitude of V initial are both 2.5 meters per second. And we're also given that the average force was 150 newtons. Okay, so now we're going to go back to this equation. And we notice it's a vector equation, which means we can apply this in the x and y directions. Okay, so let's start with the y direction. So in the y direction, this equation becomes F average y times delta t equals P final y minus P initial y. Okay, and I want to recognize this. The y direction momentum does not change in this problem. Right? We have P initial y pointing upward, P final y also points upward. So these two terms actually cancel out. They actually become 0. So that the average force in the y direction is 0. Okay, and if you think about what's happening here, this force is probably a normal force, okay, if we assume that there's not any friction acting here. And in fact, in this kind of symmetric reflection, we don't assume there's any friction, right? If there were friction here, it would actually make it asymmetric. So the force, we actually expect it to look like this, right? So this is the average force. So it should all be in the x direction, right? So let's apply this this equation in the x direction now and see if we can find the magnitude of the, well, we have the magnitude of the force, we're looking for the time. So in the x direction, we can write the same sort of thing. Okay, and P final x, P initial x, we can look at these and say they are actually changing direction, right? So when we take the difference of these two, we actually get something that is twice as big as either of them, since we expect these to be the same magnitude, just opposite directions. But we'll see that. So when we do this, we have m times v times cosine theta, right? So that's P final x. P final x is positive, right? Minus m times v times cosine theta, and that's P initial x, and it's actually negative. So we put a negative sign here. So those two negative signs cancel out, and we end up with a 2mv cosine theta. Okay, let's separate this just a little bit so it's not confusing. So that means if I solve for delta t by dividing the average force over, I can get this, 2 times m times v times cosine theta divided by F average, and I'll drop the subscript since all of the force is in the x direction in this case. So now I can just plug some numbers in. So 2 times 0.0427 times 2.5 times cosine of 30, all divided by 150 newtons, and what you get here is 1.23 times 10 to the minus 3 seconds, which is 1.23 milliseconds. And that's the time for this contact, and that's a reasonable answer.